So welcome to the series lectures of design of machine elements. So in today's lecture we are going to discuss on the design of cotter joints against the static load conditions. So during this lectures we are find out the various failures in the different elements of the cotter joints, and the objective of today's lecture is study the various failure which are present in the cotter joints based on the external loads. And the outcome of these lectures, after completion these lectures, students are able to design the cotter joints for the various applications. What is the cotter joints? So cotter joint is used to connect two coaxial rods which are subjected to either axial tensile forces or axial compressive forces. It is also used to connect a rod on one end side with some machine parts like crosshead or base plate on the other sides. It is not used for connecting shaft that rotate and transmit the torque. Is very important. It is not useful for the rotating members. It is only for the steady conditions, for tight the two conditions. The typical application of the cotter joints are like as joints between the piston rod and the crosshead of the steam engines, then joints between the slide spindles and the fork of the valve mechanisms, even joints between the piston rod and the tail or the pump rods, and it is also used in the foundations bolt. So means you can just apply the tensile forces or the compressive forces for these cotter joints, and it is useful for only this direction. It is not useful for the rotations conditions. So for the cotter joints, the three basic element is present for the cotter joints. So this, the cursor is indicate, is the socket, then the middle part is called as the cotter, and this end part is called as the spigot, and these two ends is connected with the spigot, and the socket is the rod of that the extension member. It may be the wire rope, it may be some bar, or it may be some another element is connected with the end of the socket and the spigot. And the cotter having the one side is perpendicular with the direction of the force, and one side is a slant with that direction of the support, and the slant is called as the wedge. This is the wedging action is present. What is meant by the wedging? The principle of the wedging actions is to used in a cotter joints. A cotter is a wedge shaped like this, so means is a perpendicular with this force direction and is inclined with that forces. And this wedging action, a cotter is wedge shaped piece made of the steel plates. The joint is tightened and adjusted by means of the wedge actions of the centers. The construction of this cotter joint used to connect the socket and the spigot, and between that gap you can insert this cotter. So is a typical engineering drawing of this cotter joints. There is a spigot, cotter and this pocket, and is the assembly side view of this two, and the various notation is given for this cotter, spigot and the sockets. So here D1 is the diameter of the socket is mentioned. D1 is the diameter of the socket, this one. Then D4 is the diameter of the socket collar joints. So is a D4 is the cotter socket joints is mentioned. So this one is the D4. Then C is the socket collar end thickness is given is a 0.75 D. The thickness of the cotter T 0.31. Thickness T1 is a of spigot cotter. Then D3 is the diameter of the spigot collar, T1 is the thickness of the spigot collar, A is the thickness of the cotter end, and B is the width of the cotter, and the C is the clearance. So these are the various notation is present for these cotter joints respective for the spigot, cotter and the sockets. So based on this notations and based on this nomenclatures, our aim is to find out the typical cross sections where this element is failed. And after this assembly we are apply this some external forces. The notation is given the P, and based on that P our aim is to find out the area where it's failed. So starting with this spigot, so is a free body diagram of the spigot is given. So this a separate forces is present on this spigot, there is having the tension forces P this end as well as this end, right? And what will be happens if the tensile forces is present on this? So obviously, where is the minimum cross section area is present, and at this typical cross section area, the spigot will be fail. So maximum area of this is a D, is a spigot joints, and this collar joint. So means collar is not fail. Maybe the failure occur in the spigot diameter, either maybe the failure occur in the minimum cross section. So obviously, so is a hollow cross section is present where we are going to insert the Cotter insert hollow cross section, and is a typical cross section area is there, and the failures occur at the typical zone of this cutting portions. So is the area where the tensile failure is occur. So our aim is to find out the area. So D2 is the diameter of the spigot and T is the thickness of the Cotter. So our aim is to this red colors indicate the cross sectional area where the tensile failure is occur. So our aim is to find out the cross section area by using this equation. So pi by 4 D2 square is the diameter of the spigot minus the area of the Cotter we are going to insert is minus D2 into T. So is a cross sectional area of that spigot. So we can find out the tensile failure sigma T is equal to force per unit area and is a cross section area. Then we are coming on the spigot is also fair by the shear failure, and the shear failure occurs at the plane which is parallel with the force directions. So is the plane this side and the back side of this support is the shear failures occur. So these are the two zones. This color gray color is indicate this shear failure zone. So our aim is to find out this. So is the D2 is the diameter of this spigot and A is the thickness of this distance which is from the surface of the spigot and the surface of the Cotter. So you can find out this cross section area. So is obviously D2 into A plus D2 into A. So means twice D2 into the is a typical cross section area for the shear failure. So you can find out the shear failure tau is equal to force divided by the cross section area. Then we are coming on the spigot crushing failure. So yeah, so this is a zone where the total forces acting on that the surfaces, and due to that forces maybe this zone will be crushed or it will be push in that opposite directions. So it may be crushing due to that forces, and you can find out the crushing area and is equal to D2 into T. So the sigma C is again you can say the P divided by the A. The crushing stresses is always equal to the tensile stresses in some static load conditions based on the some application. So is the CS cross sectional area sigma C is equal to D2 into T is the area, and sigma C is equal to force divided by the cross section area is a D2 divided by T. So these are the three failures occurs in the spigot. Then we are coming on the socket of that the Cotter joints elements. So is the typical joint is the diameter of this rod, the diameter of this socket, and then there is the hollow portions for the insert the Cotter. Then inside that this hollow portion is D2 is indicate the diameter of the spigot end. So the cross section is minimum cross section is present at this particular plane, and when we apply the tensile forces this area will be fail, either this cross sections is getting in failure conditions. So is a typical here the red color is indicate and the element is fail at this cross sections. So our aim is to find out this cross section area against the tensile failure. So D2 is the diameter of this spigot, D1 is the diameter of this socket, and T is the thickness of the Cotter. So you can find out the cross section area based on the equation pi by 4 in bracket D1 square minus D2 square minus again in bracket D1 minus D2 bracket complete into T and whole brackets completed. So in this way you can find out the cross section area for the socket against the tensile failure, and you can find out against tensile stresses sigma t